In this lesson, we will focus on power plants. How do we use power plants to generate energy for the purpose of electricity or heat? This will be our focus in this study. In almost all cases, the heart of power plant is a large generator that in turn uses something to spin the rotor. Sometimes it might be water moving through a hydroelectric dam or a large diesel engine or a gas turbine. In many cases, it's a turbine driven by steam, which might be created by burning coal, oil, or natural gas, or probably from the heat of a nuclear reaction. Whatever the source is, regardless of the source, the heat produced is used to turn water into steam at high pressure that is then fed through a turbine, causing it to spin at very high speed. The power generators that supply our homes, offices, and schools today are loaded with high technical equipment designed to do three important things. The first one is to optimize the combustion of fuel. Number two, to monitor the chemical content of the exhaust gases. And the third one is to keep tabs on every step of the operation. Then you want to ask yourself this question: how does power plant generate electricity? How do we get from input fuel to output electricity? One of the things I want us to pay attention to is a steam-fired plant, steam-fired power plant, as a case study or as an example. I'm going to show you the stages that occur during the operation of a steam-fired plant and the specific components for all the stages and what happens in those components, the operations that happens in those stages. We have the fuel, for example. In a steam-fired plant, we have the fuel. As the name implies, this is where the energy comes from. And the fuel could be coal, it could be solar radiation, it could be wind, it could be any source, basically. For solar, the sun is fuel that powers some kind of renewable energy technology. The wind is also fuel for other kinds of power plants under renewable energy technology. Okay, just like coal, oil, natural gas, and so on and so forth are fuel to conventional energy technologies. Apart from the fuel, we also have what we refer to as the furnace. In the furnace, what goes on there is burning. Okay, the fuel is burned to create necessary heat in the furnace. For example, this is the case with thermal power plants. And some of the fuel used in this type of plants include the coal, the gas, and so on and so forth. So we have the fuel, we have the furnace, then we have the boiler. In the boiler, the heat from the furnace flows around pipes full of water. The heat boils the water and then turns it into extremely hot pressurized steam. The steam is what we then use to turn the turbine. In the turbine, the steam is used to make the turbine to rotate, to turn. The turbine is like a fan or a windmill, but this time around it has many blades and several sets of them all stacked in a compact row. What the turbine does is to convert the steam's energy into motion or kinetic energy. And then we also have the cooling tower. We've talked about the fuel. We've talked about the fuel, we've talked about the furnace, we've talked about the boiler, we've talked about the turbine briefly. Now let's talk about the cooling tower. Once it has passed through the turbine, the steam's job is done. It then moves into a large structure where it cools down and condenses back into water before being pumped back to the boiler for another trip through the cycle. So in many cases, water is boiled, the water is converted into hot pressurized steam, the steam turns the turbine, and once the turbine turns and operates effectively, the steam job is done. The steam is then passed through a condenser. The condenser condenses the steam back to water, and then the water is passed back again into the furnace. Okay, so into the furnace or boiler. So one way or another, the cycle continues. So there's what we call a steam cycle in this power plant. And then we have the generator. The generator spins. The spinning turbine has an axle that connects it to the generator, which is where the mechanical energy of the rotation is converted into electrical energy using the process identified by Faraday. When the electricity is generated by the generator, it is then stepped up by a step-up transformer. The electricity travels out of the generator to a nearby piece of electrical equipment where the voltage is increased before it travels long distances over transmission lines. That piece or that device is known as a transformer, a step-up transformer, because it literally transforms the voltage. There are different types of power generation plants that we have. Some of them are renewable, some of them are conventional. The conventional ones include the coal power generation plants, the natural gas and petroleum power generation plants, and then we have the renewable power plants too. If you look at this particular graph, what you will see here is in this particular year, it depicts the amount of electricity generation by fuel used in power stations. You will find out that fossil fuel actually generated 53% of electricity that was generated altogether in this particular year. Now, this graph must have been updated by now because a lot has happened in the last few years, and there will be an updated version of this particular graph. So we can actually evaluate that and update this graph so we can have a knowledge. But for now, let us focus on what happened few years back and then see exactly how this played out. So you will see that nuclear generated 28% of all the electricity required for that particular year, followed by hydropower, and then we have other sources such as the wind turbines, and then the biomass, and then we have other sources of energy right up here. So fossil fuel alone generated more than 50% of all the electricity required by the world in this particular year, followed by nuclear, then hydropower, and so on and so forth. Now, when we talk about a fossil fuel, this 53% is divided into different types of fossil fuel power generation plants that we have. We have the natural gas, we have the oil-fired power plants, we have the lignite-fired power plants, we have the coal-fired power plants. You will see the percentage and shares of all of these power plants when it comes to generation of energy for that particular year. So natural gas generated most of the electricity that was generated for that particular year, and then followed by coal-fired power plant, then lignite, and then the oil-fired power plant. Now we will briefly examine how coal is used to generate electricity, how coal-fired power plants work. Now, deliveries are made regularly and the raw coal is stored at the plant in enormous piles. So there has to be a storage somewhere at a plant location where coal is piled up and stored in large quantities. Now, from that particular storage, it is crushed and sent on to temporary storage bins via a conveyor belt. These bins typically hold a 1 or 2 day supply of coal for the plant. So you can see we have coal supply here. This is coal and we have large quantities here. This is the conveyor. So you can see we have the conveyor belt right up here. So as coal is dropped on the conveyor belt, the conveyor conveys the coal right to a bin, and then the bin holds the coal and then sends it to a grinder. Now the coal cannot be used in the form it is. It has to be ground into fine powder. It has to be crushed. It has to be crushed and ground into fine powder that the machine can use. Okay, the device that does this in the power plant is called the pulverizer or the grinder. You will see here that as coal comes from the supply, it goes to the conveyor, and then from the conveyor the conveyor belt moves it to the bin, and then from there right into the grinder. So the grinder grinds the coal into a fine powder. Now it is this fine powdered form of coal that is then supplied to the furnace alongside with a lot of air. Before we go on, it is important I quickly mention some details about pulverized coal combustion. Pulverized coal combustion is the major technology used to produce electricity. The plant can have powers between 50 and 300 megawatt. It is used in more than 90% of coal-fired power plants. Coal is burned at temperatures that range from 1,500 to 1,700 for bituminous coal, which is the high-grade coal that we do know. And then it also ranges between 1,300 to 1,600 degrees Celsius with low rank coals. You can see this is a picture, an example of coal before it is being ground to powder and supplied into the furnace. All right, so let's continue with our explanation of how energy is extracted from coal and converted to electricity. So coal is burned in a boiler which produces steam. The steam is run through a turbine which turns a generator which then produces electricity. So a turbine is like a fan in reverse. It has many blades or vanes where the steam is used to make the turbine to turn or rotate rapidly. A generator is a magnet, a huge magnet that is turned by the turbine. As the magnet turns, electromagnetic field is produced inside the coil of wire and electricity is generated or produced. That electricity is then passed straight to the transformer and then transmitted to the users. So what you will see right in this diagram, you can see we've talked about this section. There are literally about 3 major sections here. The first section is the coal section, okay, where from the supply of coal we get to the conveyor, from the conveyor we get it to the grinder, and then it is ground into fine powder. That's the first section. The second section is the furnace, the burning section, and that is where coal is burnt, of course, in the presence of air, lots of air. Coal is burnt, and when coal is burnt, heat is generated. The heat that is generated then facilitates the steam cycle. Now there is a pipe, as you can see here. This yellow tube represents pipe, okay, and in this particular yellow tube, is water. Water is passed through the yellow tube, so the heat generated from the coal heats up the tube or the pipe containing cold water. Then the water boils at a very high temperature and then it is converted to steam, hot pressurized steam. That steam is what is then passed straight to the turbine. When the steam gets to the turbine, it turns the turbine. When the turbine begins to rotate rapidly, the shaft that connects the turbine to the generator automatically begins to rotate. And when that happens, it begins to rotate the magnet in the generator. So when that happens, electromagnetic field is generated in the generator, and that produces electricity right in the generator, and that electricity is then transmitted to the transformer, which steps the electricity up, and then it is transmitted to the user. Apart from the coal cycle here, the second cycle here is the steam cycle. Apart from the coal cycle, we have the steam cycle. The steam cycle, this is what happens. Steam that gets to the turbine turns the turbine, and once the turbine is turned and operates effectively, that steam has completed its job. The next thing it does is that there is another pipe right here that collects the steam and takes it to the condenser. What the condenser does is it condenses the steam into water, and then when the steam is converted into water, the water is purified, and after the water is purified, it is passed back to the furnace. It is passed back to the boiler where it comes in contact with the heat generated by burning coal again, and then it is converted back to steam, and then it completes that cycle, and then the cycle keeps going on, and then it keeps going. So we have what we call the steam cycle, facilitated by the burning of coal in the furnace. So we have coal cycle, we have the furnace and burning cycle, we have the steam cycle, and then we have the last cycle, which is the electrical energy generation from the generator and then transmitted through the transmission lines. You will find out that from the furnace we have some exhaust gases we have exhaust gases, we have flue gas cleaning here, and then we have a stack here for gas, for exhaust gas. And then we have another pipe here where we collect the ash from the burnt coal. So this is a simple schematic diagram for a coal-fired power plant. And you should be able to draw these briefly in a block way. You should be able to label this coal-fired power plant. You should be able to explain the function of each of the components labeled in these coal-fired power plant. Okay, and you should also be able to explain the entire process from the beginning till when electricity is generated, from the supply of coal to when electricity is generated and transmitted. Coal makes major contribution to electricity generation, and like we mentioned before, more than 50% of electricity generated in the world come from coal. But unfortunately, as good as this may sound, coal is the worst fossil fuel as far as pollution is concerned. The amount of gases that coal ejects into the atmosphere when it is burned is actually enormous. And these gases actually are dangerous to the health of living organisms. Hence, humans, mammals, and fishes in the ocean, and living organisms, even plants, are affected negatively from burning of coal. Replacing coal-fired by gas-fired technology would decrease the amount of CO2 emitted into the atmosphere. But in the long run, natural gas supplies will diminish. This is an advantage of gas. But then availability of gas is not as much as availability of coal. Natural gas supply will diminish over time if it continues to be used as fuel to generate electricity. So what we can do in this scenario is simple. We can learn how to use coal to generate electricity in the cleanest way possible. So this should be a subject of research, and it has been and will continue to be a subject of research. How do we continue to use coal since it is available and since it is the most available fossil fuel, and at the same time the most popular fossil fuel that we have globally when it comes to generation of electricity? How then do we use it in a way that it doesn't harm and cause hazard in the atmosphere to living organisms? Having discussed coal and how we can use coal to generate electricity in the coal-fired power generation plant, let us talk about the oil and natural gas. Oil is mainly used in transportation and in petrochemical industry. It is less frequently used to produce electricity. Natural gas is extensively used to produce electricity. The main advantages of natural gas is that it has lower environmental impact than coal. New technologies of the natural gas fired power plants are coming up. For example, the combined cycle gas turbines. What this does is that it helps us to increase the efficiency, the operating efficiencies of the gas-fired plants to between 55 and 60%. If we consider a few years ago, probably 10 to 15 years ago, the electricity produced from gas power plants are less expensive than the electricity produced from coal-powered plants. Globally and currently, natural gas has become more expensive than coal, almost 2 or 3 times more expensive than coal. And this is because the price of gas itself has increased. Availability of natural gas is no longer as it used to be. It has reduced. The price of gas has also increased. All of this put together has actually made electricity from natural gas more expensive. But then it is important to note that a gas-fired power plant emits only about half as much as CO2 as a coal-fired plant and other emissions such as dust particles and so on and so forth. This is an oil-fired power plant, and we are going to quickly look at exactly what happens. There are about 9 components in the oil-fired power plants. You should know all of these 9 components. You should know the functions of all these 9 components. You should know where these 9 components are located on the power plant. Understand the process of converting oil to electricity. Okay, as you can see, this is the oil supply, and then we have the boiler. This is the boiler here, And then we have the steam turbine. As you can see, this is our steam turbine. Then we have the turbine generator. This is the turbine generator here. Then we have, this is our supply of water. You can see this is where we get our supply of water from here. And then we have the transmission lines, the electricity transmission. You can see these are the lines right from here up here. We have the transmission to up till it gets to a distribution panel, up till it gets to where it is needed. And then we have the consumer homes and businesses. You can see we have homes, we have utilities here, we have users scattered all around. So from the distribution station, it gets to all of these users here. And then we have the exhaust stack. This is the exhaust stack. And we also have the exhaust gas plume, which is exactly what we write right at the top here. Okay, so these are some of the popular components of the oil-fired power plant. An oil power station turns the chemical energy in oil into electrical energy that can be used in homes and businesses. Oil is piped into the boiler. This is oil. It is piped through this yellow pipe here into the boiler, where it is burned, converting its chemical energy into heat energy. This heats water in pipes coiled around the boiler, turning it into steam. So you can see these pipes, and then these pipes actually carry water. So the heat then turns this water to steam. Okay. Now the hot steam expands in the narrow pipes. So when it emerges, it is under high pressure. The pressure drives the steam over the blades of the steam turbine. So these are some of the blades of the steam turbine, causing it to spin, converting the heat energy released in the boiler into mechanical energy. A shaft connects the steam turbine to the turbine generator. Hence, when the turbine spins, the generator also spins. The generator then uses electromagnetic field to convert this mechanical energy into electrical energy. So after passing through the turbine, the steam comes into contact with pipes full of cold water. In coastal stations, this water is pumped straight from the sea. As you can see right from the sea here. The cold pipes cool the steam so that it condenses back into water. It is then piped back to the boiler where it can be heated up again, turn into steam again, and then keep the turbine turning. You can see that the cycle is also repeated here, just like we have in the coal-fired power plant, especially for the steam. Finally, a transformer converts the electrical energy from the generator to a high voltage. The national grid uses high voltage to transmit electricity efficiently through power lines to the homes and businesses that need the electricity. Other transformers reduce the voltage back down to a suitable and usable level. So initially, the electricity is going to be stepped up before it is transmitted, and then when it gets to where it's going to be used, there will also be step down transformers that steps the voltage down to a suitable and usable level. As well as heat, burning oil produces exhaust gases. These are piped from the boiler to the exhaust stack. This is the exhaust stack somewhere here. They are piped from the boiler to the exhaust stack, which contains equipment that filters out any particles before venting into the atmosphere. Stack is built tall so that the exhaust gas plume can disperse before it touches the ground. You can see this is a stack right up here. It is built right up here and very high so that the exhaust gas plume can disperse before it touches the ground. This ensures that it does not affect the quality of the air around the station. So like I mentioned, you should be able to identify the components of an oil-fired power plant. You should be able to explain the function of each of these components, and then you should be able to tell us the process right from when oil is supplied to when electricity is generated and transmitted and then consumed by the users. The gas-fired power plants require smaller investments than other means of power production, such as coal, nuclear, or even the renewable energies. Again, the size of individual units can be small. The investment, operation, and maintenance costs of gas-fired power plants account for only about 20% of the cost of the electricity produced. A much larger part of the cost is the fuel itself, which is about 70 to 80%. Hence, the economic viability of gas-fired power plants is very sensitive to the price of natural gas. Any change in the price of natural gas will affect the economic viability of gas-fired power plants, no matter how little the change is. While gas-fired power plants were very competitive economically at the end of the 20th century, they are currently less so when compared to coal-fired plants. This is because, as we mentioned earlier, they are no longer as available as they used to be, so there is delay in supplying the gas. Number two, the price of gas has increased because of availability. So this put together has made it very difficult to generate more electricity using the gas-fired power plants. When we talk about natural gas or gas-fired power plants, there are different types of turbines. We have the single cycle gas turbines, and we also have the combined cycle gas turbines. The single cycle gas turbines have a very short startup time, between 15 and 30 minutes, and quick load change capabilities. They can be used to meet base load, cycling load, and then peak load demands. They are less flexible because the steam cycle operates under high pressure. Heavier duty materials are required to make this kind of turbine work effectively. Let's quickly look at how the single cycle gas turbine operates. The single cycle gas turbine is the simplest way to use natural gas. Now let us quickly look at what the schematic or the block diagram looks like. You can see we have fuel, and then you can see we have supply of air, compressed air. So compressed air and fuel are supplied to the combustion chamber. The combustion chamber is where burning takes place. That is where burning takes place. And when burning takes place, we have exhaust gases. The exhaust gases are then passed through to the turbine. It is the exhaust gases that then turn the turbine. When the turbine turns, there will be more exhaust gases produced, and then the generator would also turn. So the turbine turns and then turns the generator, and then the generator produces electricity that is required and needed by the users. So compressed air and natural gas are burned in a combustion chamber at almost constant pressure. The exhaust gases of the combustion chamber, having an initial temperature around 1500 degrees Celsius, enter the turbine at temperatures between 1200 and 1450 degrees Celsius, and then expand before they are emitted into the atmosphere at a temperature near 600 degrees Celsius. The heat content is usually lost along the line. However, it is important to note that it is possible to recover part of the heat using a heat exchanger. From what we have installed globally, the efficiency of a 40 megawatt single gas turbine is about 40%. It is a little bit less for 200 to 300 megawatt turbines, which is around 38%. Then we have the combined cycle. The combined cycle operates exactly like a single cycle up to the point where the last exhaust gas is collected and reused. And I'm going to show you why. The first cycle is what happens right at the top here. We have our fuel and our compressed air supplied to the combustion chamber. In this combustion chamber, burning takes place, and then we have exhaust gases. The exhaust gases are then supplied to the turbine. The turbine then turns and then turns the generator. The generator produces AC electricity, and that is supplied to the users, to the transmission lines. In the single cycle gas turbine, you will notice that the exhaust gases that comes out is actually wasted. It's not reused. But in the combined cycle, the main difference is that the exhaust gases that come out are actually reused. They are used again. Okay, and what are they used for? We have a heat exchanger here. They are collected by this heat exchanger, and then this heat exchanger collects the heat from the gases. This heat is then converted to steam, and then this steam turns the turbine, and then when the turbine turns, it then turns the generator connected to it again. Electricity is generated, and then steam would also be generated. The steam generated can be collected by the condenser. It is condensed into water. It is then again pumped back into this heat exchanger. When this heat from exhaust gases are collected, the heat boils water that is also pumped into this heat exchanger. It is that water that then turns to a high pressure hot steam that then turns this turbine. And then the steam that is collected after the turbine has turned the generator is then collected and pumped back into the heat exchanger. So the steam cycle continues here, and then we have the gas cycle here. Okay, so this is a combined cycle gas turbine. The exhaust gas of the first turbine, which have temperatures of up to 560 to 640 degrees Celsius, go through the heat exchanger in the combined cycle. The steam produced is used to drive the turbine. Overall, yields between 54 and 60% can be obtained in the second cycle of the combined cycle gas turbine. There is a flue gas here that is emitted into the atmosphere. Flue gas is a gas exiting into the atmosphere via a flue, which is a pipe or channel for conveying exhaust gases from a fireplace, oven, furnace, boiler, or steam generator. This flue gas refers to the combustion exhaust gas produced at the power plants. It's available when you look at the coal-fired power plants we talked about, when you look at the oil-fired power plants we talked about, and it is also available in the gas-fired power plants. So you should know what that means. So altogether, you have an idea of what a single cycle gas turbine is and what a combined cycle gas turbine is. You should be able to draw this diagram. You should be able to label the parts of a combined cycle gas turbine, and then you should be able to tell us the function of each of the components in this power plant. Because here is approximately 80% nitrogen and 20% oxygen, the high operational temperatures of gas turbines lead to production of nitrogen oxides. Nitrogen oxides can lead to nitric acid, which contributes to acid rain. The amount of nitrogen oxides emitted depends on many parameters, and such parameters include the following 5 parameters: flame temperature, fuel to air ratio, combustion pressure, and then duration of combustion. It is important to know these factors and parameters. There is a table that compares all the technologies we've talked about in details and the ones we have mentioned in passing. It compares their efficiency, their capital cost, operating cost, and fuel cost, and then the kind of emissions that they give or the quantity of emissions that they produce. This is for an earlier year, so we should find an updated version of this table for our current year or 2019. We should find an updated version of this comparison for recent years. And this should be part of the assignments, part of the projects and evaluations we should carry out in our project work. When you look at the carbon intensity of electricity generation from different types of power plants, this graph actually gives us an idea of the CO2 equivalent per kilowatt hour. You can see we have coal has the highest CO2 equivalent per kilowatt hour when they are used to generate electricity, followed by oil, followed by natural gas, and all of these three are the chief fossil fuels that we have for the conventional energy generation technologies. And then we have the solar PV, geothermal, solar CSP, down to hydro, ocean, wind, nuclear, and so on and so forth. So the carbon intensity of electricity generation is higher in coal than to hydro when you look at this data here. Let us quickly look at the characteristics of some of these power plants. Gas-fired power plants are very flexible and require less time to build and license. Combined cycle plants are the most efficient fossil fuel plants that we have. We just talked about the combined cycle power plants, and you should really know how that operates and works. The nuclear plants have low fuel costs, if not the lowest fuel cost amongst among the fuel that have been paid for. But then they are less flexible than other power plants. That's the demerit there. Coal plants require extensive emission control and probably expensive in installing. The size and cost of units depends on their corresponding power density. Fossil and nuclear plants are compact, whereas solar and wind plants can be spread out. Fossil and nuclear plants are compact in the sense that they have to be in one location, whereas solar and wind plants spread out in the sense that you can have a solar power plant in a location today, and then you can have another one in another location, and then you can connect all the electricity joined together at one point to be used by the user. We mentioned earlier that the size and cost of the units depend on their corresponding power density. So what we can do right now is quickly examine the power densities of the various fuels that we have. We have the nuclear fuel, we have the natural gas, coal, solar PV, wind, and biomass. These technologies, and these are their power densities. The highest power density we have here is nuclear, down right to biomass, which is very small, and this is measured in watt per squared meters. This is measured several years ago, and we can also find an updated version of the power densities of various power plants that we do have. This is the end of this lesson. If you like this video, give it a thumbs up. If you have not subscribed to my channel, please go ahead and subscribe right now. And also, I'd like to read from you, what do you think about oil-fired power plants, coal-fired power plants, and the gas-fired power plants? Which of these power plants is your favorite? Go ahead and comment that in the comment section. See you in the next lesson.